So let's take a look at 3.4. This section is really important. You may already be familiar with some of these. You want to be really familiar with these by the time we're done. We're going to have a quiz on this stuff tomorrow. So basically, if you look at the front and the back of this, it's got a different function for each one of these graphs. We're going to graph it. We're going to talk about domain and range, all that sort of stuff. And if you know these shapes really well, you've got like half of the homework problems done. It's literally just reproducing these particular graphs right here. And if you know them well and can commit them to memory and understand why they make the shapes they do, the ones on the front hopefully aren't very difficult. But if you understand why they make the shapes they do, you're going to be in much better condition to deal with the stuff that we work on later on in this course. Better able to deal with the stuff that comes up in 1060, and much better able to understand general behaviors and kind of the depth that we study functions when you get into calculus. Okay, so this is a really important one, and you really want to understand the details behind this. So every function makes a shape when you graph it. If you've got an equation and you graph that, it makes a shape, and we can categorize those shapes into some general categories. So the first one is we're going to call this a constant function. So we're going to call this f of x equals b. b is going to be our constant. Now, I'm going to do a numeric example for this. So we're going to do f of x equals 2. Now, if f of x equals 2, that's the same as saying y equals 2. This would be a horizontal line. It would look just like this. So there's f of x equals 2. There's our constant function. Again, it has the name constant because it's always the same. It's constantly the same function value. It doesn't increase, it doesn't decrease, it just stays constant. Now, the domain for a constant function, since there's no variable to plug in and there's no division, there's no even root, there's no logarithms, the domain is going to be from negative infinity to infinity. And in general, the range is going to be, it's 2 for this specific one, but if it were just b, it would be whatever that constant is. So I'm going to put a b there. Now, if we use this numeric example, we'd say that the range would be 2. Everybody good there? Okay. The next one is called the identity function. So the identity function is called that because whatever number you plug in, so if I find f of 5, if you plug in a 5, you get a 5 out. If you plug in a negative 3, you get a negative 3 out. So this is just a linear equation that looks like that. Again, it doesn't have any of those 3 domain issues, so the domain is going to be negative infinity to infinity. If you squish this onto the y-axis, you can plug any number in and you can get any number out, because if you plug any number in, you're going to get that same number out. So we've got negative infinity to infinity. Again, that's called the identity function. So if somebody says, hey, I'm working with the identity function, it's just y equals x. Okay? Plug in a number, it maintains its identity, it stays exactly the same. Okay, then we're going to talk about the squaring function and the cubing function, okay, both of which we've seen a little bit of already. So with the squaring function, again, I know you understand this pretty well, but let's just kind of belabor the point and make sure we're clear. This is why it makes the shape it does. It does something completely different than that identity one does. If you plug in a 0, you get out a 0 just like you did up here. But if you plug in a 1, you square it and you get 1. If you plug in a 2, you square it and you get 4. So we don't go over and up the same amount. We go over an amount and then we go up that amount squared. So if we went over to 3, I go up 3 squared. Now if I go back, I plug in negative 1. I square that, I automatically get a positive. So this is why I'm not going to be plotting numbers down here in quadrant 3. I go back 1 to negative 1, square that, I get positive 1. Back to negative 2, square that, I get positive 4. Okay? So again, this shape is one that we're already familiar with, but you want to think about and understand why it makes the shape that it does, why it has that big bend in it. This one up here was straight. This was x to the first. This is x to the second. It's got a big bend in it. Again, none of those 3 issues that we talked about, so the domain is going to be negative infinity to infinity. And the range? 0 to infinity. Why 0 to infinity? Because it starts at 0 and goes to infinity. And why don't we get any negatives? Because it's squaring. Okay? All right, let's take a look at the next one. Am I going too fast or is this okay? Good pace? All right, let's take a look at cubing. Cubing does something different. It's a different function. It's going to make a different shape, and we want to understand why cubing makes the shape that it does. So again, I'm going to plug in a 0. If I plug in a 0, I get out 0. If I go to the right one, I'm going to cube positive 1. If I take a positive, no matter how many times I use it as a power, it's going to be positive. So I end up with a 1 here. If I go to 2, I went over 2, I'm going to go up 2 cubed. So that's going to be 8. If I go to negative 1, negative 1 cubed, 3 negatives makes a negative. So instead of going up like we did on the squared graph, I go down. So this is going to be at negative 1, negative 1. And the next most convenient point would be if I plug in a negative 2, I get a negative 8. So again, notice the behavior here. This one starts down here and ends up here. So does this one. It starts down here and ends up here, but it's got a bend to it. And the reason it has a bend to it is because instead of going over and up the exact same amount, we're going to go over and up that amount cubed, or back and down that amount cubed, and so forth. So we get a graph that looks something like this. Now, if I stopped right there, everybody watch, does that kind of look like the right half of a parabola? Kind of does. Is it the same shape as a parabola? Nope. There are two things that go on here. Now, this is a detail that you want to think about why this is true. It's steeper over here than this one is. Can somebody tell me how we can tell that? How do we know this one is steeper over here than the squared graph is? Okay.
Because if you go over 2 on the x squared, it only goes up 4, but on the x cubed, it goes up 8.
Very good. And also notice this is 1, 1. That's 2, 8. It went up 7 just from this point to this point, whereas here, 1, 1 is on both graphs. It only went up to 4. It only went up 3 units as we went from 1 to 2. Yeah.
So on the squared one, it's symmetric with the y-axis.
Yes.
And on that one, it's with the order.
Very good. So what type of function is this again? We have a name for it now. Even, and this is odd, and we talked about that yesterday. Now before I finish this shape, let me point out something else. Okay, right in here. Now the way I've drawn these, it's very difficult to draw these accurately, but right in here, this looks almost the same as that. My question for you, is it? We already established that this is steeper here than this is on the squared graph. Does this look about the same? Are they the same or are they different? How many say same? How many say different? That's too bad, because nobody raised their hand for different. They are different. They are not the same shape. They are not the same shape. This one is more shallow. It's got more of a curve to it, and we'll prove this in just a second. What if I went to 1/2? If I square 1/2, what do I get? You get 1/4, right? So from 1 to 1/2, I go down to 1/2 a unit, or 1/4 of a unit right here. So we're up about 1/4. You with me? So let me zoom in just a tad on these. Okay. What if I plug in 1/2 on this one? What's 1/2 cubed? 1/8. So here's what happens with this. If we were to draw this more accurately and think about this, it's not a big deal. It's one of those details that down the road is going to be pretty helpful. This is a lot steeper here, and let me graph this. 1/8 is like this. So in between -1 and 1, it kind of flattens out. It looks a little bit more like that. Now, I've kind of exaggerated this. So it comes down here. It's a lot flatter in the middle and a lot steeper out near the ends. So like this. Hate that. Very vexing. Even more vexing. Thank you very much. Okay? All right. Any questions there? Domain and range? -infinity to infinity. Negative infinity to infinity. Because when you plug in a positive, you're going to get out a positive. If you plug in a negative, you're going to get out a negative. Any questions about that? Fine details of those particular functions right there. Now, one thing I haven't done to this point, because we've just been speeding through here, I haven't labeled any of these points. Now, I'm not going to bother labeling anything on this one or on this one. But once we get into more complicated shapes that have some curves to them, we want to label a couple of key points so we can convince people, hey, I know exactly what this shape is. So this one right here, negative 2, 4, negative 1, 1, 0, 0, where the vertex is, 1, 1, and 2, 4. 2, 8, 1, 1, 0, 0, negative 1, and negative 2, negative 8. And again, if I really wanted to emphasize the difference, you can see that this one's steeper here, but if you wanted to label a point right there like 1/2, 1/8, and right here, 1/2, 1/4, you could tell that there is a big difference between these graphs all the way along, right near the center, the vertex if you want to call it that, and out near the ends. They have fundamentally completely different behaviors. They're both power functions, but they behave differently. Okay? You ready? Listen carefully. The bigger the power, the flatter it is in between negative 1 and 1, and the steeper it is outside negative 1 and positive 1. I'll say that one more time. The larger the power, so if we did 4th power, 5th power, 6th power, something like that, the steeper it is outside negative 1 and positive 1, the flatter it is in between. If you want to have some fun, play around with your calculator and throw in x to the 100th and x to the 101st. Yeah.
So, I'm just trying to figure out how to word it. So if we went to like x to the 4th, wouldn't it look more like a parabola?
It would. Okay? So since you asked, let's think about what x to the 4th would look like. Okay? Steeper on the outside. Now, if I were to do the numbers, again, they go through negative 1, 1 and positive 1, 1, right? Okay, if I go to 2, I'd have to go up 2. 2 to the 4th would be 16. It would be way up here. Really steep, okay, and symmetric on either side. Okay, and if I took 1/2 and raised it to the 4th, that would be 1/16. So it's really steep, comes down here really fast, gets kind of flat, although not really, and then goes up like that. And again, if you don't believe me, grab your graphing calculator, type in x to the 100th, x to the 101st, and see how flat it gets. Those are a little bit extreme. They kind of go up, over, and like this. Because your calculator, because of the pixels, it can't really handle that sharp of a curve. It looks like a corner. You with me? Okay. All right. Anything else? Okay. Square root function. Let's do the domain for this one first. What is the domain for the square root function? Okay. 0 to infinity. Round around here. Square around there because it is okay to take the square root of 0. You get 0. What's the range? Yeah, you're always going to get a positive number out. The smallest number you're ever going to get out would be 0. So this is going to be 0 to infinity on that also. If you plug in a 0, you get a 0. Okay, now think about the way I've described these and how these functions behave. If you plug in a 0, you get a 0. If you go over 1, you go up the square root of 1. 1. If you go over 2, you go up the square root of 2. Well, that's a bit of a pain because that's 1.4. If you go over 3, up the square root of 3. Also a pain because that's about 1.7. What's the next nice number I could graph? 4. So if I go over 4, I go up 2. The next nice number? 9 because it has a nice square root. All the other ones are pretty ugly. It looks something like this. Again, how did we describe this the other day? Top half of a sideways opening parabola. Okay? So this is 0, 0. This is 1, 1. This is 4, 2. Again, notice I'm plugging in a number for x, and the y that I put down is the square root of that number, and this would be 9, 3. Any questions there? Yeah.
But when you do square roots, it's plus or minus the square root of the number, but because it's a function, you don't graph them negative? Is that the only reason why?
That's an excellent question. So Marissa's question is, wait a minute. It's got a square root. Don't we have a plus or a minus on there? So wouldn't we have the plus part be this part? and the minus part be this part, but we don't do the negative because we want it to be a function. Somebody want to address that? Yeah.
You can't take the square root of the negative, so that doesn't really exist there.
Okay, let's deal with that because that's a little bit of a different issue. That deals with you can't plug in a negative. That's why there's no function value over here. That's why the domain starts at 0, includes 0, and goes to the right. Christopher?
Because you didn't add the square root, so there's no plus or minus.
Okay. The only time we have to worry about a plus or minus on a square root is if we put one into the problem. So if we're solving an equation and we have to take the square root of both sides to solve it, we have to put the plus or minus in there. If there's a square root in a problem to begin with, it's always talking about the principal square root of the positive one, so we don't have to worry about that negative part. Excellent question, though. Anything else? Yeah.
Can you repeat that one more time? That kind of didn't make sense to me.
Okay. So if we were doing a problem like this, so there's a huge difference between this and this. Okay. If I'm just evaluating this one, the square root of 4 is 2. If I'm solving an equation and I have to put a square root in a problem, I have to do this to solve it, then I get an x over here, and because we put the square root in the problem, we have to account for the fact that, you know, I don't know whether this was positive or negative to begin with, because when I square either one of them, they turn out to be positive. So that's when I put a plus or minus in front of that. It's when we put a square root in a problem that we have to put the plus or minus also. This is the problem to begin with, okay? They gave us this. We didn't have to solve it to get this or anything like that. It just says graph the square root function. Because it just says square root function, it's always the principal square root. It's always the positive one. Does that make sense?
Yes.
Okay. Anything else? Excellent questions. Thank you very much. Let's take a look at the next one. Again, we knew there was a domain issue here. We knew we couldn't use all real numbers on this one because it had an even root. Do we run into that problem here? No. You can take an odd root of any number you want. So we're going to be able to plug in anything we want. I'll hold off on the range for just a second and let's go through and let's plug some numbers in. Let's think about this. So if I plug in a 0, again I get 0. If I plug in a 1, the cube root of 1 is 1. Now, if I go to 2, cube root of 2 is ugly, cube root of 3 is ugly, cube root of 4 is ugly. 8 is the first time I get a nice cube root. So if I go over to 8, I get 2. Now, if I plug in a negative 1, I can take the cube root of a negative. I just get a negative. Cube root of negative 1 would be negative 1. Cube root of negative 8 would be negative 2. So here's what the graph looks like. And I'm going to label a couple of these, negative 8, negative 2, negative 1, 0, 0, of course, 1, 1, and 8, 2. And notice that the x-coordinate, once I plug it in, the y-coordinate is just the cube root of whatever the x-coordinate is. So what's the range? Negative infinity to infinity. Okay, now I will be absolutely thrilled if we look at the two of these and somebody can tell me, you know what, this shape right here looks an awful lot like this shape right here. Is it the same? No, it's completely different. It's completely different over on this part. It's even completely different on this part. Okay, now, this is, so everybody gets the shapes, right? Have I done anything too terribly hard? I'm boring Clayton over here. He's fallen asleep. Okay? I'm just giving you a hard time. Okay. If in between negative 1 and positive 1, these got smaller. So think about this. When you raise a fraction to a power, it actually gets smaller. So if I take 1/4 and I raise it to the 8th, it becomes a really tiny number. What would happen if you took the root of a small number, a decimal number between 0 and 1? What happens to it? It gets bigger, right? And the bigger the root, the bigger it gets. So you know how this one's really steep and it comes down here and it kind of flattens out just a little bit? This would be really flat and then it would get really steep. It's going to kind of hug the y-axis rather than the x-axis. Does that make sense? Okay. Any questions? Okay. Go ahead and flip the page over. So again, each one of those has a name. You'd want to know the names. On this back side, we're going to talk about the reciprocal function, the reciprocal square function, absolute value function, greatest integer function. And then I think to end with, we deal with a piecewise function. All right? So let's do the reciprocal function. Do we run into any issues with this? John? You can't plug in a 0, right? Is there anything else that you can't plug in? No. So the domain's going to be everything except for 0. Everything else is okay. Now, let's stick with what we did before. So I'm skipping 0, but I can plug in a 1. What's 1 over 1? 1. Plug in a 2. 1/2. Plug in a 3. 1/3. So the bigger number I plug in, what happens to the value of the function? It gets smaller and smaller and smaller. Okay. Now, does it ever reach 0? It doesn't. So what we have here is a horizontal asymptote. Now, let's focus on right in here. Let's plug in small positive numbers. Small positive numbers. So let's say I plug in a 1/2. Let's say I plug in 1/2. It's a reciprocal function, right? That's the name of this function. What's the reciprocal of 1/2? 2. Reciprocal of 1/3? 3. Okay, now, let's plug in a really interesting number like 1,000th. If I go 1,000th on this side of 0, how high up do I have to go to get on the graph? I have to go to 1,000. So the smaller number I plug in, the bigger the overall quantity gets, so I get a graph that looks something like this. Okay, that's the reciprocal graph. Yeah.
What if you plug in a negative for x?
We're going to get there. Hang on a second. Okay? So the name of this is the reciprocal. What's the reciprocal of big positive numbers? Small positive numbers. What's the reciprocal of small positive numbers? Big positive numbers. You get it? So if I plug in a -1, I get -1. So now we're getting to Parker's question of what happens if you plug in a negative. Let's do the easy ones first. If you plug in a -2, -1/2, -1/3, -1/4. So if you plug in a big negative number, you get a small negative number. So this has a horizontal asymptote on both sides of y equals 0. And let's do it this way. You with me? I'm going to plug in small negative numbers. What is the reciprocal of a small negative number? A big negative number, right? It's not going to change the sign. It's just going to be a big negative number. So it's going to go down like this. So because it has this asymptote right here, because it approaches the y-axis, I have a vertical asymptote of x equals 0. So it has two asymptotes on there. Now, the last thing we need to fill in on this is, what is the range? Yep. You can get any y you want out except for, see, now it's freaking out. 99% of my CPU usage. That's crazy. Anything but 0. So it looks like I'm going old school again. I can't tell you how this hurts. Okay, so let's take a look at absolute value. Let's do that one next. Does anybody know what the absolute value function looks like?
Yes.
See this? It's a V shape, right? So whatever number you plug in, you get the exact same number back. So if you plug in a 1, you get out a 1. If you plug in a 2, you get out a 2. But it makes sure that it's positive, right? So if you plug in a -1, you get out a +1. So it's basically perfect 45 in and perfect 45 out. So the domain and the range, the domain. Do we have any of those domain issues we talked about? Nope. So all real numbers from -∞ to infinity. What about the range? 0 to infinity. Now, round or square around the 0? Square, because it does actually hit 0, right? Okay, any questions there? Nice little V shape. You want to remember that one. That one comes up enough that you want to know what that one is. Okay? All right, let's take a look at the reciprocal square graph. Oh, let's see, maybe I'm back. All right, now this one is different than the one up above. Can somebody tell me one thing that's different about this? You don't have any negatives. You're never going to get a negative out of this because the top's positive and the bottom's also positive. Okay, that's something that's different. What's something that's the same? Can't be 0. So we're going to throw out 0. And we're going to say, you know what? Up here, you could get out positives and negatives. How could I say I only get out positives? 0 to infinity. So it's going to look something like that. Everybody good there? Okay. So if you plug in some numbers, now let's just think about this. If I plug in a 1, I get 1, because 1 over 1 squared would still be 1. If I plug in a 2, I get 1/4. Okay, now up here, up above here, I plugged in a 2, I got a 1/2. Plug in a 2 here, I get a 1/4. So it gets smaller, it just does it faster. It gets smaller, quicker, would be a way to say it. Everybody got that? But we're still taking the reciprocal of a small positive number, so that's going to be a big positive number. And what do I get on the other side? A flipped image. I'll take that. Even though that doesn't look like -1, 1, I'm going to make it -1, 1. Okay, we do want to label a couple points on these. And again, if we were to say key points on this, you're probably really only going to graph a couple of these points, maybe one on each one of those branches, if you will. Should I label anything else on this? Are there any other important features? Clayton? Asymptote. Give me one of them.
Vertical at 0.
Okay, we've got a vertical asymptote at x equals 0, and we've got a horizontal asymptote at y equals 0. It happens to be the same asymptote on both sides. Okay, everybody good with that? Okay, watch. Everybody done writing that down? So you can think for just a second. I'm going to rewrite this one as 1 over x. That graph right here. So it's going to have this basic shape. Isn't that the same thing? Are these two things the same? I hear some yeses and nos. Guess which one's right? Oh, see, that's disappointing.
What is it?
These two are the same thing. They are the same thing. So if I were to take this shape and square it, it's going to change its shape a little bit, but definitely the biggest change is going to be all of these answers that used to be negative. What happens when I take negative values and square them? That's why this side flips up here. That's why this piece looks so drastically different than it did before. Because when you square it, it becomes positive. Now, does the shape change a little bit? You bet. It gets smaller quicker because of the squaring. You with me there? Do you see how this hugging down closer to the x-axis faster? Remember that whole thing? If you raise the power, if you raise the power on a tiny number, it gets smaller faster? Okay, all right. Okay, now, this is the last one we're going to take a look at, and if I have time, I'm going to do another example besides this one right here. For some reason, people struggle with piecewise functions. How many of you have graphed piecewise functions before? Okay, all right. Then hopefully we get it right the first time, because I think if you pay attention to the way I explain it, I think you'll be in pretty good shape there. All right, so let's take a look at the greatest integer function. This is an oddball function. It comes up occasionally. These are actually used. Some mathematician didn't just think, hey, I'd like 1050 students to really struggle with a function, so I'm going to throw this at them. That's not the way it worked. There are functions that actually display this type of behavior. Okay, so this is called the greatest integer function. Sometimes it's written like this, and sometimes instead of being called this, it's called a floor function. Okay, you might hear both. Greatest integer is usually how it works. And this is the way the greatest integer function works. And I'm going to use an XY table for this just to make this clear. If I plug in a number, so let's say I plug in 0. When I plug it in, this says, find me the greatest integer, positive or negative whole number including 0, that's not bigger than the number that I just plugged in. So what's the biggest integer that's not bigger than 0? 0. Okay? Let me do another one. Let me do 0.5. What's the biggest integer that's not bigger than 0.5? It's 0. Okay, what are the two integers that are closest to 0.5? 0 and 1, right? 1's bigger than 0.5, so you can't use that one, so you have to use the biggest one that's not bigger than that, so that's going to be 0. Okay, what about 0.9? Also 0. What happens the second I plug in a 1? I get a 1. Okay, so this would be 1. So I'm going to blow this up just a tad. And here's what I get. All the points from 0 all the way up to here are all 0. And then the minute I get to 1, I jump up to 1. Well, let's think. If I plug in 1.5, what's the biggest integer that's not bigger than 1.5? 1. So all the way in between 1 and 2, all the way up to 1.9999999, it's 1. And then the minute I get to 2, I jump up to 2. And then I go like this and like this. Okay, so forgive me, this isn't a great graph, but that's the way it is. Yeah.
So you don't round when you're doing this?
No, you don't round. Nope. You don't take 1.99999 and say, oh, that would round up to 2, so I'm going to use 2. Okay, you look at the number and you say, you basically take off the decimal part if we're dealing with a positive number. Yeah.
So just kind of looking at your graph. So when we make those lines, the last circle has to be open.
Yes, it does, because the minute you hit this one, the minute you hit 1, you jump up to 1. The minute you hit 2, you jump up to 2. The minute you hit 3, you jump up to 3, and so forth. Is that okay? You know, this is usually what gets people. This is called a step function for obvious reasons. Okay? What gets people is this problem right here. So I'm going to change colors. So this makes, what if I do negative 0.5? Don't say anything out loud. I want you to think about what is the biggest integer that's not bigger than negative 0.5. You've got two choices for integers that are right close to negative 0.5. They are negative 1 and 0. What's the answer? McKay?
-1.
It is negative 1. Okay? Now, that should be a little bit comforting, because if I graph that at negative 0.5, I'm down here like that. It keeps this stair-step pattern. So this would be open, closed, open, closed. Looks like that. Okay? You with me? Now, here's where it gets really interesting. What three functions have domain issues? Even roots, division, logarithms. Is this any one of those? It's not. So guess what you can plug in? Anything you want, all reals, negative infinity to infinity. Now the range, that's another story. What is it? All integers. All integers. Because if you think about this, if we were to squish this onto the y-axis, this point would be covered, this point would be covered, this point, all the integers would be covered, nothing else in between would be covered, because the answers that come out of this function are all integers. That's why it's called the greatest integer function. Okay? Weird function, comes up occasionally. Can anybody think of an application where you'd have a function that doesn't just kind of rise and fall, but jumps like this? Yeah.
Maybe it's like you can't take half something.
Mm-hmm.
So
That would work. There's a commercial on TV where some guy's buying insurance and he goes into a store and he rips a loaf of bread in half,
Oh, yeah, that
starts tearing stuff out of packages and things like that. You don't get to do that. You buy the whole thing or not. If you have like a data plan or something like that, or a cell phone plan, you don't get to pay things by that fraction of a minute, they're by the minute. So if you go over and it's 20 cents a minute, it's going to jump up 1 minute, then another minute, then another minute. There's nothing in between that. Does that make sense? So these do actually come up. They can come in handy. They're not nice, but they come in handy. Okay, any questions? Okay, now let's talk about a piecewise function. Before we do, are there any questions on anything we've gone over so far? Sure? Okay, yeah.
Are we gonna go more in depth with each of these and future chapters?
I thought I was doing a good job.
Yeah, but I mean, like, the equation.
In what way?
This slows, if it's
We do that in calculus. Yep. You want to take that right now?
maybe.
Okay. We do that in calculus. In the next section, we're going to take every one of these and we're going to do transformations with them. So we're going to slide them left, right, up, down, stretch them, shrink them, all that sort of stuff. Okay, so we will use them again. That's why, but for right now, it's just got to know the shapes, the basic shapes. Okay? All right. Anything else? Okay, this is called a piecewise function, and it's called a piecewise function because it comes in pieces. Now, if you had to guess, how many pieces do you think this function has? Three. Three pieces. Okay, this is the function, and I'm going to call it the shape. This is where it looks like that shape. Okay? So if we said this in technical terms, this right here is the function that we're going to graph, and this is the domain for that function. You with me? Okay, now here's how I like to do these. And if you like writing in pen, that's not a good idea for this, so I would always use a pencil, especially for piecewise functions. I'd use a pencil always in math. So take a look at this. Do you know what this shape is right here? What shape is it? It has a name. It's called the identity function. It's a very easy graph. It's a line that goes through the origin with a perfect 45. Slope is 1 over 1, right? So we're looking at this shape right here. So I'm going to do this. That's the shape. Don't do that if you had a pen. So this is the right shape. Where does it look like that? Where what is less than 1? X, where X is less than 1. Now notice, the other day I said if somebody says where does something happen, that's an X. If they say what is it, that's a Y. Well, what is it? It looks like this line. Where does it look like that line? Whenever X is less than -1. So -1 is right here. So that kind of divides this thing in two. It only looks like that over here. It doesn't look like that over here. So I'm going to erase part of this graph. What part am I going to erase? I'm going to erase the greater than side. I'm going to erase this. Now I put this little line right here just so I could have a dividing line. I'm going to erase that. I'm going to make that a solid line. I'm going to put an arrow on the end. And now I need to put a circle on the end here. Is it an open circle or a closed circle? It's an open circle because that -1 is not included. If I'm at something other than -1, okay, or if I'm at -1, it's not here, it's somewhere else. It's one of these other three pieces, it's one of these other three shapes. You with me? Okay. What shape is this? The word is constant. It's a 2, it's a horizontal line. So we've got 3 good descriptions here. So I'm going to do this. Oh, come on. Okay. Now, is there any way I can keep all of that horizontal line? No. I've got to erase this part, right? Because if I kept both these, this wouldn't pass the vertical line test. So where does it look like that? Between -1 and 0. So I'm going to erase this. I'm going to erase this. almost. Here's where. So there's no way out there because that's the vertical test. So I'm going to cross this. I'm going to cross. The only place where it's on the line is between -1. Okay, now I need to put on it with the points. There's the first. There's X. There's the second. There's 2. What's that piece look? Look at this. Switching the press. It looks like. Am I going to keep it all? Nope. I can look at this and I can say, well, look, it says X has to be greater than 0. So it only looks like that when X is greater than 0. So I'm going to erase this side, and clearly I'd have to erase this side just so it could be a function, right? And I'm going to keep all of this open circle. Okay, that's it. That's how you do it. Range.
0 to -1.
Careful, careful. Squish it here, I'd have all of this covered. Squish it over here, I actually double cover this little bit right here, right? But that's okay. But then there's this little gap that isn't included. So it would be from starting at -infinity, going all the way to -1. Open or closed? Open. Then union, where do I start up again? Start up again at 0 and go to positive infinity. Good? Easy enough? Okay. Then let me give you one similar to what would be on your assignment. This one's only going to have 2 pieces though. So this is going to be graph it and figure domain ranges. Like what we said, it's easy if you go step by step. There should know the shape. So I'm sitting on that paper there. Okay, x cubed looks like this, right? What part of this graph do I keep? The one that's less than -1. So on the left or right? left side of -1. So I'm going to erase all of this. I was going to erase all of this. You're just going to keep this piece right here. Open it up. This looks like that. I'm only keep from 4, which I'm going to keep from here. Over there. So that's what. And this point, it's not filled in, but it's 4, 2, and this point right here is -1, -1, right? So the domain, -infinity to -1, union, 4 to infinity, range, sweet, 2, 2 infinity, right? You with me there? Okay. Can you tell me what f of 9 is?
3.
Why? It works on this one here, but think about this. If you plugged in a 9, you've got 2 choices. Is it this one? No, because 9 is not less than -1. 9 is greater than 4. So you plug it in here. Square root of 9 is 3, meaning it's on this branch, it's on this piece, it's on that shape. You with me? Okay. You think piecewise functions are tough? I hope not. Okay. If you've got a question on any of this, come and see me. You're going to have so if you look at the homework, we did like half the homework for you right now. Get the homework done. Come tomorrow ready to graph any one of those along with 3, 4, 5 key points on those functions. Understand those shapes, why they make the shapes they do, and you're going to be in business. Have a great day.